Hello everyone, welcome to the Bitflip Academy. So today we are going to discuss about the linker script. We had some overview in our last discussion about the linker script, but yeah, today we will see in depth what is the linker script, what is the use of the linker script, and what are the syntaxes we use in the linker script. If you remember from the previous lecture, this is the flow diagram of complete build and then flashing. So in this sequence our linker comes here. So this is our linker. So what linker does is linker takes the object file and it takes the linker script, and based on these two inputs it generates the .elf. So what is the object file mainly? So the object file is the files in which your different sections are defined. The different sections we have. So all the functions will go to the .text function. All the global variables will go to the .data section. All the uninitialized variables, global variables, it will go to the .bss section. All the const variables, it will go to the .txt section, right, which is raw data. Raw data goes to the txt section. So these are the different sections we have in one object file, okay, and linker identifies these sections, okay, and based on the linker script what we provide, it assigns the address to those sections. So which section will go to which address. So before going ahead with the linker basics, I would like to show you what are the things we have in the object file. So let's try to visualize the object file. So this is our example project which we are taking. Inside this project, if you will see, in the build folder we have different object files for the different source files: clock, config, delay, GPIO driver, main. So for all these we have different object files. Now let's try to visualize what do we have inside one object, the dump. Yeah, so if you will see, this will show us the content of the dump file. So in the content of the dump file, if you will see, these are the sections, different sections we have. Usually we learn about these some of these sections in our C programming. So .text section we have, .data section we have, .bss section we have, and some debug related sections we have. If you will see here, currently sizes are defined for all the sections. So .text section size is 60, .data section currently there is no data, global data, .bss currently there is no uninitialized variable, so these are 0, 0. So this is VMA, virtual memory address, and this is LMA, load memory address. So virtual memory address is the place from where our code will execute, that section will execute basically, and the load memory address is kind of permanent memory, from where it will get load, so kind of flash memory. Usually we load the code, data, everything into the flash memory, and based on the requirement we can copy it from the flash memory to the virtual memory or the RAM. But in the addresses, so VMA and LMA, if you will see, both are 0, 0. Both are 0, 0 means why it is 0, 0? Because we have not allocated the address for these sections currently. And how we do it? We do it using the linker file. As now we will continue the basics of linker script. Now if you will observe the linker script, so first thing you will see is the entry reset handler. So what is the entry reset handler? Entry reset handler is nothing but it indicates that what is the entry point for the code execution. This reset handler is mainly meant for the different softwares we have in our compiler, you know, the compiler package basically. So we have the object dump, object copy, then we have the debugger. Okay, so these softwares generally uses the this entry symbol. Okay, so they don't know you know, from where the execution will start, so they will look for this entry symbol basically, and this is part of the ELF header basically. So now after the entry symbol we have the E stack. E stack means the starting address of the stack, or in other way the end address of the RAM basically. So this E stack is a symbol how, you know, how we derive the E stack address is basically, so the starting address of the SRAM and plus length of the SRAM. So when you will add the length into the starting address of the SRAM, you will reach to the end of the SRAM. So end address of the SRAM. So that end address we basically assign into the E stack symbol. Okay, and this E stack symbol is again the part of vector table. Now after that you will see we have something called the memory command. So what memory command is for? Whatever the types of memories you have in your microcontroller, okay, whether it is a flash memory, whether it is a you know, RAM memory, SRAM, or it is a TCM, tightly coupled memory, or it is a maybe CCRAM, something, whatever you have. Okay, all those type of memory, if you want to use in your code, so you have to define, you need to define those memory here in this memory command. Okay, then only later you will be able to use those memory basically. So you know, you will be able to decide, okay, in this memory my code will go, in this memory my data will go. Okay, so those kind of decisions you will be able to make only when you will define that memory into this memory command. So the memory command defines physical memory region for placing code and data. Each region has a name and an attribute. Attribute is like RX, RW, a start address origin, and a size length. So size and length is pretty obvious. Every memory, for every memory there will be a start address, you know, and that we call origin here, and for every memory there will be a length, you know, some memory length will be there, memory size. What is the attribute? So attribute, if you will see here, we have something called X, R, W, something like this. Okay, so we have like X, we have R, we have W. Attribute is nothing but you know, it's a kind of permission. Okay, so what is allowed for that memory and what is not allowed for that memory basically. So X means execution. Execution means code execution is allowed or not allowed. If you are defining the attribute X in the attribute, means code execution is allowed from this memory. R means read. So whether you can read that memory or not. W means write. So whether you can write to that memory or not. Okay, so these are the attributes basically. So if you will see in the SRAM we have XRW. All the attributes are here in the SRAM. Okay, it means from the SRAM I can execute the code, I can read the SRAM memory, and I can write also into the SRAM memory. But in the flash memory, if you will see, we only have the R and X, we don't have W. Why? So because from the flash memory we execute the code. Okay, we only do the read operation. Where we keep our code? We keep our code in the flash memory. Okay, and if you will give the write permission to the flash memory, then what will happen? It may, you know, maybe by mistake we can damage our code basically. Okay, suppose if there is some issue of the, you know, dangling pointer, or some by mistake from the code we are trying to access, you know, we are trying to modify the flash memory. If you will give the write access to the flash memory, then what it will do, it will basically destroy your code, you know. So that's why usually for the flash memory we don't give the write access. Okay, if you will try to write into the flash memory without the attribute, then what will happen, it will trigger an exception, some memory exception or memory fault exception it will trigger. Okay, so this is about the memory reason. So yeah, these reasons are later referenced using the what you can see, the greater than symbol and reason name to map logical memory sections. So obviously, so this is, we have the physical memories, right? So SRAM and flash are the physical memories. Now in the physical memories we can have multiple logical memories or logical sections basically. Okay, so those which logical section will go into which physical section or physical memory, that we can decide using this symbol that we will see just after this. Okay, so yeah, so this was all about this memory section. Okay, now after the memory section we have a command called section. So this is a section command. What section command is, generally, so all the logical sections we define inside this section command. Okay, so if you will see, the section block maps logical section, example text, data, to a physical memory region. So whatever the logical sections I want to have in my in my project, all those logical sections I will define inside this section command, and those logical sections then I will map to some physical memory or some physical memory section like SRAM or flash. Okay, it controls the memory layout of the final binary, crucial in embedded system. Obviously, the memory layout will be decided using this section command only, inside this section command only, because the sequence, what sequence you will follow inside this section command, the same sequence will be followed into the physical memory. Okay, so if you have kept your vector table first here, in the section command, if your vector table is first, then in the physical memory also, in the vector table will go first. In the starting address your vector table will be there. Okay, if you have kept your reset handler function after the vector table here in the section, then again your reset handler function will go after the vector table in the physical memory. So what I mean to say here is, suppose this is the section command, this is the section command, and what I have done is, first I have kept the interrupt vector table, this is a logical section. Okay, then maybe I have kept the reset handler. Okay, after that maybe I have kept the default handler. Okay, so this one. So now sequence, if you will see, this first is the interrupt vector table, then reset handler, then default handler. So when it will go into the flash memory is nothing but our physical memory section. So in the flash memory, since here IVT is first, so in the flash memory interrupt vector table will come first, then your reset handler will come, and after that your default handler will come. Okay, so like this. So this is how the section impacts the memory layout. Okay, so that's what it is trying to say. It controls the memory layout of the final binary. See some of the logical section inside the section command. So first logical section is interrupt vector table, ISR vector. Okay, so this is nothing but the interrupt vector table. So what we have done, we have defined the interrupt vector table first in the logical section. Okay, so in the interrupt vector table, if you will see, this is nothing but the section name. Okay, this is the name of section. Okay, this double colon indicates that start of the section basically. Okay, so now start of the section, this is name of the section. Okay, and then inside what we have, the first thing you will see is dot equal to align 4. Okay. So what does it mean? Here the dot operator works as a address counter basically. Okay. So dot operator works as a address counter. So you can imagine dot, here the dot is a kind of variable. Okay, this is a kind of variable which gets updated every time. So more and more memory you will allocate, the more and more addresses, address will increase, and that increased address will be inside this dot operator basically. Now after that we have the align command. So what align command does? Align command aligns the starting of any logical sector according to the hardware needs basically. Okay. So suppose for the STM32 microcontroller, STM32F407 microcontroller, the alignment requirement is 4 byte or 8 byte. Okay. So what this align will do, align 4 means align 4 will align this section, start address of this section will be aligned with the 4 byte. Okay. So if you will see, suppose you have an address 0808000003. Okay, this is one address. Okay, if you will see, this address is not aligned to the 4 byte basically. Okay, so what is the meaning of aligned to the 4 byte? Means it should be divisible, the address should be divisible by the 4. Okay, if some address is aligned to the 4 byte, means that address should be divisible by the 4, and here you can clearly see this address is not divisible by the 4. Okay, so it means even if this address is available, okay, even if this address is available means empty, even if this address is available or empty, but linker will never use this address. Okay, will never use this address. Why? Because here my alignment requirement is starting of the sector. Okay, this is the starting of the sector. So my alignment requirement is 4. Okay, so what is the next address which is aligned to the 4? The very next one, 8000 and then 0004. Okay, so this is the address which is aligned with the 4 byte. Okay, so it will use this address, the next address. So that is the meaning of this aligned operator here. Okay, and what will happen when this section will be allocated? So the address will start from the 0800004. Okay, so this address will, this dot operator, okay, this guy, this dot, okay, so this dot will have this address basically. Okay. After the align, what do we have? We have something called keep. Okay, so this is keep. Okay, so what is the meaning of the keep command? Keep means simple. In the English, what we have meaning of keep? Okay, keep means you keep something. Even if I am not using this logical section anywhere, then also you keep it. That is the meaning of keep. Now the question is where this section will go. Okay, I have defined the section, I have defined everything, I have defined the alignment and everything, but where this section will go, in which physical memory this section will go? So it will go into the flash memory. So how we can make sure that? We can make sure using this syntax, if you will see. Okay, so greater than and then flash, assignment operator basically, assign and flash. So it is assigned to the flash memory. For example, let's say this is your flash memory. Okay, this is so this is my flash, and I already assigned one section here. Okay, currently my dot will be equal to 0x080000. Okay, Now what I did is, after that I assigned one interrupt vector table, IVT, okay, IVT section in the flash. Now what happens, my this much area is full, right? So now from here we have I have the empty area basically, okay, from this address, okay, this address could be anything, maybe 0x8100, something like this, okay. So what will happen now, after this, this dot will update, okay, and this will update to 0x8100, whatever we have, okay. So that's how this dot operator keeps count of the available memory basically. So next what we have a logical section, the reset handler logical section basically. So since the reset handler, now we have to define the reset handler function, okay. Previously in the interrupt vector table, what we define the symbol basically, just a variable which keeps the address of the reset handler, okay. But now we have to define where in memory my reset handler function will reside, okay. So reset handler function is nothing but it is a code, so it should go to the text section. That's why we added a one .txt before the reset handler section name. So again align is there, keep is there. What is the meaning of this asterisk here? Asterisk is here is basically the it is a wildcard symbol basically, okay. Wildcard symbol. Wildcard symbol means, so any code, any data which is under .txt .reset handler in any source file, in any object file, okay, in any object file, that should come under this section, okay, that should come under this section. So this is what the wildcard symbol means, okay. So we have multiple source files. In the multiple source file, we have lots of functions, we have lots of variables. So some of the functions, maybe some of the functions is assigned to this section basically, .txt .reset handler, okay. So those functions, maybe some of the variables are assigned to this this section. So those variables, all those code and all those variables basically will come inside this logical section .txt .reset handler. Everything is same, so it is going to the flash. This is our default handler, okay. So now let's see what we have. We have the .txt section, okay. As we already know, what type of things go into the .txt section from the C programming basics, we already know, right? So functions, all the functions will go into the .txt sections. Raw data means const variable, all the const variable will go into the .txt sections, okay. And .txt, but we have another asterisk here, okay. Another asterisk means any section, okay, which starts with .txt, okay, ending could be anything, but the starting should be .txt, okay. Any section that can be, suppose txt, I don't know, underscore, we can say like some function 1, okay, .txt underscore, maybe we can have the const data or rom data, rom1 something, any. So any section which starts with .txt, okay, and could be anything, if it is defined anywhere in any of the object file, that section should come under this section. So constant means the constant variable which we cannot change. So we have to keep our constant variable in a place, in a memory where we don't have a write access, okay, and that is only one memory is there, flash memory, okay, where our code goes. So we can keep the .text section inside the .text section basically, raw data. Now what we have here is this one, underscore etext equals to dot. So as we have already discussed, what dot operator does here, dot operator always keeps the latest address basically, okay. At this line, what will happen, your this .txt section started from here, okay, and it ended here. After the end, okay, what is the next address, what is the next available address, that will come into the etext. Suppose your section is ending ending at what to say, the 0x800, maybe, you know, 0008. So since we are ending the .txt section at address 0x8000008, okay, then what will be the next available address? Okay, so whatever is the next available address, even according to alignment also, that will go and store into the underscore .etxt. Okay, so next available address, that will go and store into the .txt. Why? Because the dot operator always points to the next available address, empty address. Okay, now here in this syntax, what we are doing is, at this place we are doing the load address. So load address usually we do for the flash memory basically. Okay, so we load some address from the flash memory, and since the dot data section we are storing into the flash memory, and then during the runtime what we are doing is we are copying it to the SRAM basically. Okay, so that's why at this line we are getting the start address of the data section from the flash memory. Okay, so this will be flash memory load address. Address of dot data section. Okay, so how generally it works is, suppose if you have this flash memory, okay, this is your flash memory, okay, and then we have RAM here. Okay, so this is our RAM. So what will happen, in suppose in the flash memory somewhere we have this you know, dot data section. So this is nothing but the dot data. Okay, so in the RAM also there will be one dot data section. Okay, dot data section, and this will get copied. This will get copied during the runtime from the flash memory to the RAM memory. Okay, and this one is nothing but the VMA, virtual memory address, and this one is nothing but the LMA, load memory address. Okay, so here what we are getting is using this load address, so we are getting the starting, address of the LMA. We are getting the LMA from where the data section will start. Means if you consider your, you know, this flash memory starts with 0x8000000, so this is the starting address, start of dot data. So this memory you will get here in this syntax. Okay, and we are storing that memory into the SI data, and after that our data section starts. Okay, it can be anywhere, it can be before the data section definition also, it can be after data section definition also, not an issue. So now after that our data section starts. Okay, this alignment is we already know what is this alignment. Okay, and this one what we are doing is, again this is your you know, address operator basically. Okay, so dot operator. So here what we are doing is, since this data we are copying to the VMA, virtual memory address. Okay, so here we are taking the address of virtual memory address, not the load memory address. Okay, so here we are taking the address of the VMA. So starting address of the VMA, virtual memory address, is RAM. So in the RAM, so suppose if RAM, you know, RAM start address is this one and end address is this one. Okay, so this address, this one we are loading here, the VMA start address of data section. Okay, and same here we are loading the end of the VMA end, and this is start. Okay, VMA start. And yeah, this symbol, if you will see, this is something using which we define the we define where this section will be where this section will store permanently, and from where we have to load it. Okay, so start. So this symbol means at the runtime this section will be in the SRAM. Okay, and this one means it will store. So we will load from okay, so we are loading it from the flash memory basically. So that is what the syntax, how the syntax looks like here. Okay, and then we have the .bss section. Okay, so .bss section is nothing but the uninitialized data. So uninitialized global variable, all those will go into the .bss section. So here also we don't have much. If you will see, alignment is there, and then the start address, since it is going into the SRAM, so it will have the virtual memory address VMA, and then again this wildcard symbol, take all the .bss section from all the object file and put inside this BSS section. Then again this is the end of the VMA. So VMA end, and it is going to the SRAM. So currently these are all pretty much these are all the sections we have in our project. In our current project we don't need this one basically, because we have not defined any section extra. Okay, apart from so in all the object files, all the text section is in default area, which is .text basically, default section. So yeah, this is our linker file. If you will see, so we have the entry reset handler here. So we have the start address of the stack pointer, and then we have the memory section, SRAM, flash. Then we have the section command, inside which we have defined all the sections. So this is the interrupt vector table, ISR. This is reset handler. This is .txt, and then this is our data, SI data, and this is our .bss. Yeah, this was all about the linker. At least this much should be enough for you to start working. Even you can modify this linker according to your need basically. So yeah, thank you for watching, and thank you for your patience.